Page 25 is the end of chapter 1. We're going to start with some vocabulary, starting off with relation. A relation is a set of ordered pairs. Usually what you will see with a relation is a group of inputs and a group of outputs, and the relation maps one input to an output. So you can express a relation in lots of different ways. For instance, the example I'm giving you right now is a relation that is a set of 3 ordered pairs. I have these curly brackets. We call those curly brackets set notation. This actually has 3 elements in it. Those are the 3 ordered pairs. A function is a special type of relation where all the inputs or x values are unique. For instance, if I were going to give you something like this, 1, 2, 3, 3, 5, 9, -2, 10, and I asked you if this was a function, the thing that you would want to pay attention most to is the x values. The y values have nothing to do with it. You're just looking at the x values. And if all x values are different, 1, 3, 5, -2, then you can say, yes, this is a function. So here's a couple examples really quickly, looking at different ways that you can see functions, because functions or even relations can be expressed as like a table, set of ordered pairs, a picture, a graph. There's lots of different ways to show relations, and we'll have an opportunity to look at all of those different ways. For A, you have to examine all of the x values to see if they're all unique. In this case, they are. So we can say yes, A is a relation. For B, again, I'm going to look at all the x values. Notice that 2 repeats. I have 2 twice, so this is not a relation. And I'll even write on here that the number 2 repeats. C, my inputs this time are going to be expressed on the top row. And so 1, 2, 5, 7, those are all unique. So we're going to say, yes, this is a relation. For D, 7, 8, 7, I can stop there because even though I have more than 1 repeat, all it takes is 1 repeating input value, and then it is not a function. The relationship between Monique's age in days and her height. If you think about this, if I were to make a table here that talks about how old she is and her height, how many days old she is, let's say I'm talking about day 1000 and then day 1002 and then day 1004 and day 1005. Notice that I don't even have to write heights in here because I know that no days repeat, because this is not Groundhog's Day. In the real world, no days repeat. So we would say, yes, this is a function. Sometimes you'll see a relation and it's expressed as something that's graphed on the x and y axis. When we have that type of situation, we use what we call the vertical line test. The vertical line test basically is when you take a vertical line and you slide it from the left to the right over your function. And since I don't think I have the ability, oh, I do, I'm going to move the words too, but that's okay. If I go ahead and slide my vertical line along my relation, as long as it's only touching it at one spot at a time, once, 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 then we can say yes, yes, this is a relation, a function. Yes. If I make another vertical line here, I'm going to have the same kind of situation. It's hitting it once everywhere, so we're going to go ahead and say, yes, this is a function. I'm going to make my vertical line here. I don't even have to slide my vertical line along the graph because I can see right away it touches the graph twice, and that is going to be not a function. It can only hit it once at a time when you're sliding your vertical line from the left to the right. You can see this again here, not a function. For D, if I go ahead and I put my line there and I move things, you can see that it only touches it once at a time. So we're going to say yes, this is a function. And for E, again, if I just draw my vertical line anywhere, no circle is going to be a function. So we're going to say no, because it's going to intersect that circle twice. It can't. If I think about it now, the one type of function that is always going to be a function is a line, as long as it's not a perfectly vertical line. Every other line besides lines that are perfectly vertical are considered functions, because you can't make a line curve onto itself or have it have any corners. So that's an interesting thing to note. Go ahead and pause this video for a few moments and determine whether or not A, B, C, D, E, if they are functions or not. So I'm going to ask you to pause the video and then come back in just a moment. Okay, so if I look at A, I have Mary, Mark, Carla, Fred. Mark repeats, not a function. B does pass the vertical line test, so we're going to say yes, it's a function. C does not pass the vertical line test, so this is a no, not a function. D is just a bunch of different points. Notice that if you look at these points, if you were to draw a vertical line, these would not pass the vertical line test, so this is not a function. E is a function. If you go ahead and draw a vertical line, move it from left to right, this would be a yes. All of the X values are unique. For 1.7 on page 28, we're going to look at a different topic for a moment. We're going to talk about function notation. This is something you're probably a little bit familiar with, but just as a little bit of a recap, if you've seen different symbolic phrases that are describing the relationship between two variables, one way to do that is to use X and Y. For instance, when we were graphing lines, we used Y equals mx plus b. And if we put numbers in for M and numbers in for B, then you would have some kind of statement that showed an input and an output, and that's how we've been working on this so far. When you use function notation, that's actually just a different way of writing the relationship between two variables, but instead of drawing a Y, you're going to draw something along the lines where you have a letter that represents the function, and usually by default that letter is F. And then whatever we're using as the input variable goes inside a set of parentheses next to the F. The way to pronounce what's going on here is the F of X is 2X plus 9. If you were going to say that verbally, that's how that would be. The thing about functions is it doesn't always have to be F. For instance, I have here 3 different examples of functions. One is defined by F, one is defined by G, one is defined by H. And each of them have a different rule that if you were to put an input into it, it would do something different to the output. For instance, F would take the input and multiply it by -3 and add 5 to it. If I were plugging into the H of X, it would square the input, multiply it by 4, subtract 19. They do different things. The thing with function notation that's kind of interesting is that it's very quick for someone to be able to identify the function that they want you to use and the input they want you to put in it. So f of 7, if I go ahead and I bring down my f, what I'm going to do is I'm actually going to write the entire rule, but I'm going to leave the parentheses blank. Definitely write the parentheses, because sometimes it's a game changer if you don't. And then wherever I see x, I'm going to actually plug in the input variable that they gave me. In this case, it was 7. So if I simplify this, -3 times 7 is -21. Combine that with 5. If I input 7 into F, my output is -16. If I was going to express this as an ordered pair, 7 is replaced for X and -16 would be the replacement for Y if you were going to do that. So it makes you think that before we were looking at ordered pairs like X, Y, input, output. Well, now we can say X, and instead of putting Y, you would see F of X, whatever the output is after you plug that into F. For B, you're looking at H3, and H is defined by 4x squared minus 19. Where there is an x, I'm going to plug in 3. If I use PEMDAS or the order of operations properly, the first thing I would do would be squaring 3. Then I would be multiplying 4 times 9, which is 36. 36 take away 19 is 26, 16, 17. So if I input 3, my output is 17. C and D are really interesting because they're asking a different thing. They're asking you to find X. They're giving you what the output is, but they're asking you to find X. So for g of x, if I have g of x equal to 2.5x minus 9.7, I haven't found x. I've got to leave x there, but I'm going to set this equal to what they are telling me that this is going to be equal to, 12.3. And then I'm going to solve for x by doing everything I would do whenever I am solving an equation for a variable. So I have 2.5x equals 22. And then I'm going to divide both sides by 2.5. Go ahead and cancel that over here. If I put that in my calculator, x is going to be 8.8. Basically, if I have a ordered pair, 8.8 as an input would give 12.3 as the output. The last one is D. They're asking us to find x if the output is 11. So I'm going to say negative 3x plus 5 equals 11. Go ahead, subtract 5 from both sides. It gives us negative 3x equals 6. If I divide both sides by negative 3, x is negative 2. My handwriting is awful. There we go. Okay. When I'm looking at relationships, a lot of times you'll always see a pool of input values and a pool of output values that you're using for whatever it is that you're trying to use as the two variables. Some people would identify that pool of input variables as the domain. So basically the domain is all the x values or input values in a relation. Notice I didn't say function because it's possible that there's a relation that isn't a function. Not all relations are functions, but that's a thing. The range, all the y values in a relation. You're basically listing these out. So if I was asking you for A to give me the domain, you would say, open your curly brackets, 1, 5, 7, 15. If you were asking for the range, that is going to be all the y values, 3, 7, 9, 17. All the y values. Go ahead and pause for a moment. I want you to identify the domain and the range. Use the set notation with the curly brackets. And then you can unpause, come back, and see if you have the same thing that I have. For C, the domain is going to be 1, 2, 5, 7. The range is going to be 3, 5, 12, 17. For D, the domain is represented by the age of the student. I have 6, I have 7, I have 8, I have 9, I have 10. Notice that even though I had repeats in my input variable, I didn't repeat them when I was listing out all of the possible x values. I only have to write them once. The range here is first, second, third, and fourth. Let's talk really quickly about domain and range when you have a graphed relation. We're going to use something that we call interval notation. Notice today I've talked about interval notation right now. I've talked about set notation when you're using curly brackets to identify elements. I used function notation when I said the f of x. So we're using this word notation a lot, which is kind of like a way of presenting something. Interval notation uses parentheses and brackets to express a range of values and whether or not the start and end point is included in that range of values. Important to know that a lot of times infinity is a thing when you are putting the range down. Brackets matter. If you have the squared brackets, that means that the end, the start, or I should start and or end point is included. If you have parentheses, that means the start and or end point is not included. Anytime you have infinity, it has to have parentheses with it. You can't pinpoint an end point or a start point with infinity. So that's a thing. So let's talk about B. If I'm looking at the domain of this, remember that the domain is the x values. So I'm asking how far left to how far right I'm looking. I always have to start in my range of putting the smaller value and then ending with the larger value. This goes forever and ever and ever in the direction of left, and forever and ever in the direction of right. So I'm going to have infinity for my domain, but I have to express it properly. So I'm going to open my parentheses, and I'm going to say that this comes from negative infinity and it goes to positive infinity. I'm using parentheses because I have to use parentheses. It's the only way I can express infinity. Then if I'm talking about range, range is the y value. So I'm talking about how far down to how far up we're going. Notice that lines, they come from negative infinity, and even though it's slow, they are increasing forever, so they're going to go to positive infinity. So I'm going to express my range the same way that I expressed my domain. For the next example, I have a circle. This has a very clear domain. It starts at -2 and it ends at +2. This is how far left and how far right this relation is stretching on my graph. So, and these are included. So I'm going to say bracket -2 to +2, close bracket. They're included. If I was talking about the range, that is literally how far down to how far up we are going. This also starts at -2, it's included, and ends at +2. It's kind of the nature of a circle. This last example, what I'm going to do is I'm actually going to tell you what this point is. This point is going to be represented by the number 4. This point right here is going to be represented by -3. I'm going to find the domain first. Remember, the domain is how far left to how far right. If I look for the domain, this looks like it's going to be from negative infinity to positive infinity. If I'm looking for range, remember range is how far down to how far up. Range is including the points. I'm assuming that these hit -3 every time. I'm assuming that these hit 4 every time. I'm going to say bracket -3 to comma 4, close my brackets. The smaller value, comma, the larger value. It is possible for you to be looking for the domain and the range of something that has one bracket and one parenthesis. So that's possible. I will show you really quickly what that looks like. Here is a graph. It has, I'm going to put something like this, and I'm going to say that this is 1, and I'm asking for the domain. The domain is how far left to how far right. This starts at negative infinity and goes to positive infinity. The range, that is how far down to how far up, starts at 1, and the 1 is included, and goes to positive infinity, and positive infinity has to have a parenthesis. So it's possible to have a bracket and then a parenthesis. Anytime you have infinity, you should always use a parenthesis. And this is the end of section 1.7.